Coherent mapping uses anatomical data and the LET data of all collected points to create a global pattern of activation in the chamber of interest. To do this, Coherent separates the entire map surface into many equilateral triangles that are invisible to the user, all with 3 mm sides. The LAT value of each triangle is then calculated using the LAT values of its included points. In this example, triangle 1 has an average LAT value of minus 90 milliseconds. Triangle 2 has an LAT value of minus 88 milliseconds, and triangle 3 has an LAT value of minus 75 milliseconds. Since triangle 1 is earlier than triangle 2, which is earlier than triangle 3, Coherent knows that the vectors must be moving from triangle 1 to triangle 2 to triangle 3. In addition, Coherent knows the amount of time it takes to move from one triangle to the next. In this example, Coherent determined that the first vector is faster than the second vector. This same calculation is run over the entire map surface to determine the vector velocity and directionality among all triangles. In the case of complex fractionated signals, Coherent utilizes wavefront to identify all possible sites of annotation and then considers the global pattern of activation to determine which annotation is correct. Any outlier vectors are identified and removed. Coherent also applies logical and anatomical constraints on the vector map. The algorithm tries to keep each triangle as similar as possible to its neighboring triangles. No sharp turns allowed. Coherent then uses user-defined scar tags and anatomical structures to identify areas of non-conductivity. In addition, double potential tags, conduction velocity slower than 10 centimeters per second, and vector collision are used to calculate areas of slow or no conduction, or snow zones. When these concepts are applied to a broader area, snow zones and anatomic structures combined with vector directionality and velocity creates a coherent map to better describe arrhythmia circuits and their critical isthmus. In this example, Coherent displays the entire circuit from early to late activation. Coherent vectors and propagation show the progression of the tachycardia circuit around a snow zone. Ripple can be played simultaneously with Coherent to reinforce the circuit path and slow conduction regions. Bold vectors, seen here, indicate slow conduction velocity. The coherent calculation is run over the entire map surface, which is invisible to the user, and results in a clear final map that provides a global solution to better describe arrhythmia circuits and their critical isthmus.